Thank you. Thank you very much. Well, good morning. So, as was mentioned, my name is Derek Ferguson. I'm head of engineering for JP Morgan Chase's commercial bank. And today we will talk through TensorFlow for Java developers. So, before I get started, just a show of hands, how many people have worked with TensorFlow before? Okay, just a few. How many people have worked with any kind of machine learning? A few more. How many folks have worked with Java? Excellent. All right, that's a good start. So that's really the only skill set that you need for this presentation. Let me start by sort of setting the stage here. So the request. Your business wants you to investigate machine learning. You know, they've seen it on television, they've heard it on the radio, they're sure this is the next big thing. They want you to find a suitable problem within your organization for machine learning. So find the problem and then solve it. But the challenge is we assume no prior background in machine learning. So we'll go through very briefly what machine learning is in this session. Then we assume no prior background in advanced math or data. So when you start to study this area, the vast majority of documentation that's out there starts from a perspective of advanced math and theory, and then it works towards the practical. We're actually going to work in exactly the opposite direction this morning. I'll start from the practical, and then we'll get a little bit more into the mathy stuff, but not too deep, I promise. So like I said, very pragmatic, quick intro to machine learning. Then an equally pragmatic, quick intro to TensorFlow. So, why TensorFlow? TensorFlow can be made to work with Java. It requires some effort, but we'll see how to do that. And it's sort of, it's becoming a de facto standard just in terms of usage out in the community. It's originated by Google. It's an open source initiative, so it's got a lot of traction. There are other things out there, obviously, but that's what we'll choose in this session. And then we'll do 4 live Java coding demonstrations. So if you like an element of risk in your presentations, hopefully this will satisfy that need. So what is machine learning? All right, so I like to think about it in, these are sort of like the most simplistic terms. This is how I explain it to like friends and relatives who aren't in computers. So you teach a computer to solve 2 + 2 - 1, simple arithmetic, right? That's been around since Charles Babbage's analytical engine in terms of computer capabilities. 2 plus fill in the blank -1 = 4, algebra. I think Babbage's analytical engine was even able to do stuff like this, or maybe it came in a later version of, big machinery-based computers. That's been around for a long time. 2, 3, 1 is inputs. Give me the 4. A computer being able to go in and actually fill in those operations, that's where you start to get into machine learning. By providing numerous data examples of inputs tagged with outputs, and having the computer inductively reason, okay, if I see this set of inputs this many times paired with this set of outputs, I will eventually, through machine learning, be able to tell you this is the pattern, this is the model that you need to use in order to produce these outputs out of these inputs. Now, this has a very sort of close relationship with the scientific method. So, imagine that the business problem that you're coming up with is something about like, customers and the products in which they might be interested. So you have a theory that based on a bunch of factors about your customers, you can deduce the products upon which they might be interested. Okay, fine. So that's sort of your generalized hypothesis. What's the first thing that you're going to do in order to work this out? You're going to want to get your hands on a bunch of information, a bunch of data about your customers and the products that they've historically shown an interest in. That's your training data. Now, there winds up being an interesting thing. It's sort of like this rule of thirds, where what you will typically do is you'll take the set of training data that you have, which is typically a rather large set, and you'll divide it into thirds. The first 2/3 you put through your inference engine, which will be TensorFlow for us, as we'll see shortly. And the inference engine uses that 2/3 of your data to devise a proposed model. So it keeps seeing all of these pairings between, all right, customers of this type seem to be interested in these products, customers of this type seem to be interested in these products, so on and so forth. Therefore, I think the model that would explain this behavior is as follows. You've used 2/3 of the data at your disposal at this point in time. Now, what you basically do, you're ready for the experiment. You use the last third of your data to go through and say, all right, if this is what I think my model is, let me pass my last third of data through that model and check it. Because in this case, I have both the inputs and the outputs. And let me see if the outputs from my model match reality. To the degree that you see that that's the case, that's the accuracy of your model. So that's sort of like testing your hypothesis in the scientific method. All right. So I think I mentioned in passing a lot of data. Folks who know hardly anything about machine learning have just through osmosis, I think, realized, all right, there's some connection between big data and machine learning. Let's talk about why it is that you need that much data. So once again, very simple example. In fact, this has got to be the simplest machine learning model that you can possibly have, right? Two operands, two inputs, and one operand method. 0 and 0 producing 0. Could be multiplication, could be addition, could be subtraction. We're not sure. We add in a second data point. By the way, I love this one. 1.5 and 3. Everyone sees it, and the first thing that you think is, well, all right, so it's addition. But of course, then you think about it for 2 more seconds, and you realize, well, no, that could be multiplication also. Okay. So we've eliminated subtraction at this point in time. Finally, we get a 6 and a 7 producing a 42. We've narrowed down, okay, this simple model seems to be multiplication. But in actuality, one thing that tells us that's not nearly going to be enough for us to have a reliable model, even for this case. We need exponentially more data to really build some certainty that, yes, we're really talking about multiplication in this case. That's already an exponential need. Now think about a more real-world example. In a real-world example, this would be considered a very small model even. And I've actually gone through the legwork of checking this out. There are tons of ways to produce -2 out of the values on the left. It gets to a point very quickly where in order to use an inference engine, you need reams and reams of data to really build a reliable model. Thus, the relationship between the recent surge in interest in machine learning and the slightly less recent surge in the availability of big data technologies, one is really the enabler for the other. The fact that we can now tap into huge amounts of data is the reason that machine learning, which has been, the concepts have been around for decades and decades in academia, this is the reason that it's now actually practicable and being used by lots of folks in sort of mainstream computing. The next objection that I often tend to hear in discussing these things is, well, you know what, the data that we're looking for is non-numeric. All right, there's really no such thing as non-numeric data. Let's suppose that you were working in the area of health surveys, and you suspect that there's some relationship between like smoking and health issues. You would probably send out a survey to get people's health behaviors, and then you'd look up to find out what their health histories are and find out what sort of conditions they've had. You can take every question on that survey and you can encode the answers to it as numbers. 0 equals no, 1 equals yes. You can then encode their health outcomes as numbers also. It's very straightforward. Images and time data are just number matrices. Let's talk about time data. Let's talk about the example of you want to be able to predict when an airplane is going to have some sort of serious mechanical issue. There are thousands of sensors in a modern airplane, right, on every apparatus within the airplane, and they're constantly sending back telemetry. You can take feeds, you can take samples from that telemetry at different time intervals. Those become your rows in a matrix, and the individual monitors become your columns. That's a matrix. I threw this slide in for 2 reasons. I'm going to go out on a limb and think pretty much everyone in the room knows that images are basically matrices also, but besides demonstrating that with an image, this is an example that you will see when you start looking into TensorFlow in depth right off the bat, I promise. It's called the MNIST data set. It's 60,000 handwritten digits each of which have been electronically tagged with what that digit is. It's used all over the documentation as a good sort of starter training set. And the fact that 60,000 is kind of useful because it makes the rule of thirds pretty, 40,000 for training, 20,000 for testing your prediction afterwards. All right, so what is TensorFlow? TensorFlow is an open source C++ library for Java. So right off the bat, and the fact that it's not a Java library in and of itself, not ideal for our purposes, but it's really, it's nothing too stressful. You've got J and I, there's all sorts of different ways to get into C++ code. The wrapper that has been built for it is Python. I say 90%, really think 90% plus. When you go out and you look at the documentation, pretty much all the documentation is about Python, Python, Python. So Java integration requires craftiness, or at the very least it requires being very good with Google and being able to piece together a bunch of stuff on stack trace, which hopefully this presentation will save you from having to do that. Let's take a step back and talk about how the name sort of relates to the underlying functionality. What are tensors? So tensors were a previously existing concept in mathematics. They have types. They have ranks, which is a fancy word for a number of dimensions. And they have shapes, which is the size of each of their ranks, aka the size of each of their dimensions. So let's see that with just some simple examples. So if you've got a rank 0 tensor, that's a scalar. That's 3 or negative 7.5 or what have you, single value. Rank 1 means you have an array. And since you have an array, for the very first time, you have to provide a shape in order to describe this also. So rank 1, shape 5, 5-element array. Pretty straightforward. Rank 2, shape 3, comma 3, got a 3 by 3 matrix. Piece of cake, right? A little more about tensors. Tensors may be contained in TensorFlow by variables. This is super useful because if you couldn't change the value of tensors, you'd never be able to evolve your model, right? You'd have to guess it the first time and then it doesn't add any value at all. So variables, important. Those variables can be mutated by operators, operations. So the operations are the things that will actually go in, and as you pass data through your model to try to train it, these are the things that will influence how those tensors get changed to be an accurate model to reflect your situation. Now, tensors, variables, and operations are the three kinds of things in TensorFlow that are contained by a graph. And a graph, think of it just like, a database for tensors and variables and operations. So why is it called TensorFlow? Well, the technical reason is that this representation is what's known as a stateful data flow graph. As a simpler way of thinking about it, when you create these graphs, which are these databases of your tensors, and you connect to them with a session, you start feeding your training data through it. It's basically thought to think of it as flowing through your tensors, and as it flows through the tensors, they evolve and mutate their values to match the data that they're seeing, so they give you a nice model that's truly representative of your underlying data. I think we already talked about tensors trained via mutation of variables. Models make prediction after training. That's the whole reason for doing this, right? You don't just create the model and then say, oh, that's great. After you have the model, you want to be able to give it to folks or use it yourself to make predictions. If we stick with the example I had earlier of customers and their interest in products, it's not so much for historical reasons that I'm going through and saying, okay, what products have different kinds of customers been interested in. It's probably because in the future I want to say, okay, I know you're a customer of this type, therefore I'm probably going to market the following products to you. That's the name of the game, right? So what we're going to see in the first live demo is the absolute simplest thing I could think of just to make sure that TensorFlow is set up once you get your hands on it. Two tensors, x and y, connected by an addition operation. So what we're going to do is we're going to connect to TensorFlow from Java. We'll put in 2 values. We'll ask it to add it, give it back to us. It can't be anything simpler than that, right? All right, so how are we going to make the connection? There's a TensorFlow Java SDK. It's available as a Maven dependency. This is one of the few things out there I'll say just works. Basically, you take that, you put the entry in your pom.xml file, it goes. Also available in other formats. There's a Gradle version of it, I think. TensorFlow-Lite also allows basic TensorFlow on Android Java, but I'm not going to speak to that at all in this session, just calling out that that's also another variant of Java that has some TensorFlow for it. So here's the crux of the presentation and what we're going to be spending the next 45 minutes on. The Java SDK only wraps about 20% of the TensorFlow classes. So the good news here is that the 80-20 rule does apply. You can do about 80% of the stuff with 20% of the classes, but once again, we're going to have to be a little bit crafty with some of this. That leads to the question, what's in the 20%? Basic model creation. Well, that's good. We want to be able to create models. Model training. You can train the models. Excellent. Inline predictions, meaning that once you have that model, you can load it into your Java process space and say, hey, give me a prediction based on the following inputs, and it'll give you back the response. And predictions across the network. So if you have different infrastructure that you want to run your TensorFlow infrastructure on, but you want to run your Java over here and just make a call to get predictions, that's all supported also. So what could possibly go wrong with any of this, right? All right, so what are the classes that we're going to see in demo number 1? org.tensorflow.tensor, generic type. This is really the underpinnings of everything. Very nice that they've chosen to express this as a generic type in Java, because it means you can use that same class for any sort of underlying primitive that you want. Output. This is the class that allows us to reach into a running graph and examine the values that are in it. For example, the answer, the prediction that we want. Graph, as I already mentioned, think about this as like a database of tensors. And session. So if the graph is your database, the session is your connection to the database. Nice analogy. All right, so it's showtime, demo 1. So note, I'm running on VirtualBox. I found that setting up TensorFlow in a development environment is very easy on Ubuntu. A little more complicated on Mac OS. So if you have the option, I would go with this. This is our source code. Let's talk through this a little bit. To begin with, note, so I've added in the library. At this point, it's just an entry in pom.xml. I import the org.tensorflow.star package. That's good. That's all you really need to do there. Main. Spin up a graph. So now we've got an empty database, quote unquote, ready to hold our tensors. And I've got 2 helper operations that we'll look at next. One adds constants, and it takes a reference to the graph, a nice human-friendly name that we would like to refer to the tensor as that we're going to add, and a value, which in this case will be 2. We call the same thing, we give it a name of C2 and a value of 12. Okay. Then we add an add operation, we pass in the graph, plus the 2 tensors that we just created to say, okay, this operation is going to run on these 2 tensors. Fine. Then we spin up a session against that graph, and we use the runner method on our session, which is just a built-in, to fetch this operation directly out of the setup graph and run it and get back the first value that it produces, which is going to be 14. I considered making that an audience question to see if anybody could add 2 and 12, but I'll skip over that and just say it's going to be 14. If it isn't, then there's a real problem with my demo. So let's take a quick look at the helper methods. We'll go with add constant first. So Add constant starts by calling the create method on the tensor class. Nice factory method. You pass it in the value, it gives you back a tensor. And notice it'll type it for you. So that's great. Really, really, really important that you understand at that line of code, you have a tensor, but it's not in a graph. It's useless, okay? So this is sort of a stumbling point for, because folks, well, I've got a tensor. It's not associated with the graph yet. After you create the tensor, you have to use an op builder operation off the graph, tell it the type that you want, which in this case is going to be a constant. Remember, it could also be a variable. The type, which you can take directly off the tensor, and the value, which is going to be the tensor itself. You call build on that. That puts the tensor in. Then you call output, which gives you a handle back, which we're going to want because we need to return it. Then add operation is very similar. But because this is an operation, we don't need to create a tensor for it. We just call g.opBuilder with the add-in, give it a friendly name like the big adder. We add the two tensors in this case that we passed in as inputs. Once again, build it, meaning putting it in the graph, and then we output it so we've got a handle to it. So that's all the code. Let's go ahead and run this and see what sort of a day I'm going to have. All right. So the good news is we got back 14. That would be a problem if we hadn't. Let me call your attention to this red text here, because I guarantee you when you run this, so try, if you remember anything out of this presentation, try to remember this bit, because you will see this and it will panic you at first. So you see this red. All this is telling us is when this TensorFlow binary was built, it was not compiled to use the instructions, some of the special instructions for my simulated CPU. On a development desktop, this could not possibly matter any less. If you're going to production, obviously, this could be very substantial to you. Particularly if it's in your training environment, you're going to want a binary that's optimized for your CPU infrastructure, because remember, you're going to be passing tons of data through this. Every millisecond is going to count, right? But on a development desktop, when you see this red, don't freak out. All right. So let's do something a little bit more interesting. Let's imagine the case where you want to do some sort of a health survey of the relationship between cigarette consumption and CHD deaths per 100,000 within a certain age group, all right? So the first thing you do is you try to get your hands on some data about adult cigarette consumption, and then you'd want to get your hands on some data about deaths. And what you do is you plot the thing you know, or the thing you're going to know in the future when you go to make your predictions, across the x-axis, and you plot the thing you're going to want to predict against your y-axis. So if we did that for this underlying data, and I just pulled this off the internet, we can see it's got a nice, cloud shape that goes from the lower left-hand corner up to the upper right-hand corner. So we look at this and we think to ourselves, well, what would a model that was able to predict the number of deaths based on cigarette consumption, what would that look like? Obviously, the answer is we'd want a line that goes through that data as much in the middle of all of the dots as possible. Now, I know I sort of promised at the outset we wouldn't get into math. I promise this is the absolute most complicated equation we'll have in the entire talk. Y equals mx plus b. So this is that's how you express a line, with y and x basically being the data points you pass in, and then your m and your b values being the slope and the y offset. So the question becomes, how can we get ourselves into a situation where by poking in all of these different data points, giving that to TensorFlow, TensorFlow can set the line for us, aka this is known as linear regression. So that's evolving model. When a class that adjusts the model to fit the data, that's moving the line into position. TensorFlow provides the gradient descent optimizer. Actually, it provides a few classes that do linear regression. Gradient descent optimizer is like I guess the big one, that fits 80% of your use cases. So that's great. Of course, it's not in the 20%. I mean, you would have guessed that, right? So what do we do about this? Well, one of the nice things about TensorFlow is that all of the underlying data structures, everything that's in a graph, everything that goes across the wire, et cetera, is stored in protobuf format. Now, I'm not going to get into the details of protobuf, but it's basically, it's a Google binary standard for communication and storage, and typically you have a protobuf definition file that defines your data structure. Then there are code generators for all sorts of different languages that can take that file and give you, code in those languages that represents that data structure, which you can use to encode it or decode it. So from all sorts of different languages, you can put stuff into files, send them across the wire, so on and so forth. You can download a binary of an untrained GDO model online with no problem. There are many places that have just put untrained gradient descent optimizers online, specifically because they realize folks that aren't using Python don't necessarily have direct access to this. We said it stores protobufs. Just in case everything else were to change between the time I created this deck and the time I'm giving this presentation today, I went off to Apogee and I actually wrapped a little Python script for everyone that you're welcome to use. And basically, you pass in 3 values, I give you back a starter gradient descent optimizer model. You provide the initial slope. You provide the initial y-intercept. You can see those at the end of the URL here. And you provide the learning rate. So slope is pretty obvious. Y-intercept is pretty obvious. What's the learning rate? The learning rate is closely related to a question I suspect might have occurred to many of you when you realized you had to provide initial slope and y-intercept, which is, I thought that TensorFlow was going to do that for me. Well, it will. So where to start? Now here's the thing. If you were actually going to go out and try to do a model that related smoking to health issues, chances are you probably already had some sort of gut instinct about what you thought you were going to find, right? That's the case with pretty much every model. Folks don't start their research without any sort of opinions on what they're likely to find. So by choosing a starting point, all you're really doing is reducing, potentially, if your guess is correct, the amount of data that you need to use to get your model in line and the amount of time that you need to run your training. Of course, if you make a bad guess, it's going to take even longer. So if you don't know, if you're really just sort of fishing out there in the data to find out what sort of patterns might exist, you can start with a flat line. That's fine. Flat line in the middle of your data set. That will work. The learning rate is the thing that is going to determine how much TensorFlow moves the line with each new data point you provide during training to get a model that matches your data. So folks hear this, and the first thing you think is, well, I'm going to set that fairly large because I want to get this done quick and I don't have much data. Thing is, you don't want to set it too large. Let me show you why. So in this case, let's imagine that the line was originally horizontal and we poked in a data point that was sort of high. The line has jumped from horizontal clear over that data point because it moves by the amount of the learning rate. Now we poke in a second data point and it sees, oh, all of my data is beneath where my line is. Let me adjust downwards by the amount of the learning rate. And now you've got a line that's completely on your data set. Then you put in another data point and it's above. And so when you set the learning rate too high, you can get into a situation where a linear model never can intersect with the data because the granularity is too large. The fancy name for getting a line that goes through your data, by the way, is having your model converge. So don't set it too large. Set it low and have lots of data. And if you don't have lots of data, a way that you can cheat is by repeating the data that you already have multiple times into an inference engine. That will bring down your reliability overall, just so you know. So it's better to actually have lots of data like any sort of scientific study. But just as a practical note, there is a way to cheat if you don't. So let's see what happens with a low learning rate. Data point moves a little. Another data point moves a little more. Another data point moves a little more. It's sort of like watching ice melt. Once you get enough data, the line goes straight through the middle of it. It's not doing this thing where it's jumping over and down and back and sideways and all that sort of stuff. Let's do demo number 2. In this, we're going to take a look at graph importation. So remember, we just went out to the internet. I didn't actually just go out to the internet. I did this before the presentation. But theoretically, we just went out to the internet and we downloaded a model, which I think I set with a slope of 5 and a y-intercept of 3. We'll see shortly. So we're going to see how we can import a graph that we downloaded. We're going to see placeholders, which are special kinds of tensors that don't have initial values. They expect to be fed values in as a part of training. And we're going to see feeds, which is the way that you push data in. And that's that. So all right, so here I moved from just using the asterisk to calling out the classes specifically. No shocking difference there. I could have just continued to use the asterisk, but first thing I do has nothing to do with TensorFlow other than the fact that the file that I'm reading into this byte array is that default gradient descent optimizer model that I talked about. Notice that the extension is .pb. That means it's a protobuf. Or at least that's the reason that it has a PB extension by default. Or it contains protobufs is probably more accurate to say. We spin up a graph just like we did before. We spin up a connection called a session to that graph. And the first new thing we see is import graph def. So this takes that default gradient descent optimizer I created and loads it into our graph. Okay? Now, this next line, I know I said, if you remember anything, remember the thing about the red error or the red warning that we had before? I'm going to change my mind. That would be the second thing. The number one most important thing to remember is this line here, because without this, everything will work fine in development. The first time you run this in production on a server that stays up between training cycles, you'll get bizarre behavior you won't be able to explain. This is TensorFlow EASE for reset everything to the initial values. So, sort of my hard luck story on that is the first time I loaded TensorFlow onto Lambda, and I tried to do multiple trainings between it, because Lambda instances will stay up for a little while. You can keep the machines warm. I started getting bizarre behavior with that. So this is a very important line at the start of any training. Then we have a helper method called print variables. So let's take a quick look at that. So print variables goes into the session and it fetches 2 tensors with special names, wread and bread. That's your slope and your y-intercept. Then we get the float values out of them and we print them out. So this helper method just it's going to let us look into our graph periodically during training and see where our line is at. So then up here, how are we going to do the training? We're going to do it in 5 batches of 500 each. And basically what I'm going to do is I'm going to randomly create an x value, and then I'm going to compute what the y value should be in order for it to be along a sort of idealized line with a slope of 3 and a y-intercept of 2. So basically, if you imagine it, all of our data points are going to be along this hypothetical line that we want to convey to TensorFlow, hey, this is really where you should move the line in order to be aligned with our data. You'd never find something this idealized in the real world, but for this demo, it'll allow us to see exactly how the line moves and the speed and all that sort of stuff. There are 2 other specially named tensors, input and target for this, which correspond basically to the x value and the y value. So we're going to call the feed operation on the runner. That's how we actually push our training data in this case. And then after every 500 examples, we're going to take a peek and see where our line has moved to as a part of training. When we're done with training, I call toGraphDef, which takes my graph and puts it back into a binary array. And then I just use standard Java to write that out into another file. So this is how you can take an untrained model, train it up, and then put it back into a file to put it on other systems or to give it to coworkers or whatever, all in Java. Last thing we do, remember I talked about the rule of thirds here? Well, this isn't a third, we're just going to do it with 1, but basically I'm going to pass in the value 1, and I'm going to ask for a prediction using basically fetching this output tensor. And if we feed in a 1, and if the model is properly trained, it'll be 1 times 3 plus 2. In other words, we're going to get back 5. So let's give this a run, see what we get. Okay, so my starting line that I downloaded had a W of 5 and a B value of 3. It needed to get to a W value of 3 and a B value of 2 in order to match what we said up here was the data that we were going to be poking in. So it does a good amount of movement with the first 500 data points. It gets to 3.5 and 1.5 rounded. And then in the subsequent 500 batches, it refines that position until finally, after 2,500 data points, if I pass in a 1, I get back a 5, essentially. All right. So let's see. So that's demo 2. How are we doing on time? 11:06. So, yeah, we're doing pretty well. All right. So the next concern that you should probably have is not everything is a line. And I gave just one example here of something not being a line. Participation in the labor market. You start off in school, then you're in the labor market, then you retire. So that's clearly not a line. Linear regression is not enough for that reason. Training to recognize addition versus subtraction. So I tried to think, what's the next sort of level that we could take this to? It seemed like passing in data and having it recognize whether something was addition or subtraction might be sort of the next step in this, and it does not work with linear regression. Basically, what we're going to do is we're going to pass in values A, B, and C, and have it predict whether A and B were added or subtracted in order to produce C. This is sort of like one of the examples I showed at the start. I've used the example of health surveys many times. If you give, if somebody says, they're 22 years old, they drink once a week, they smoke 10 cigarettes a day, and, it turns out they've got diabetes or whatever, feeding in that sort of input data with that sort of an outcome, you've got 3 data points you're feeding in. It's not going to work great with linear regression. Recognizing images. How would you put an image, if you're trying to get it to recognize images of birds, for example, how are you going to put that on the line? It doesn't make sense. So the key to this, and the next thing that we almost always study in machine learning, is something called neural networks. So what is a neural network? And this is one of these instances where the concept has been around in academia as something that could be done for decades, and it's only fairly recently that we've got the computing power and the data assets to actually be able to do it. It's modeled against the human nervous system. You start off with 86 billion neurons in your brain. You end with 86 billion neurons in your brain minus, whatever you've killed off with lifestyle choices and that sort of stuff. What changes over time is the ability of neurons to connect to each other. So, for example, the neurons you have in your brain that, and in fact this is true of all mammals, that are specialists in smell, very good at making connections with the neurons in your brain that are responsible for things like memory, which is part of the reason why everybody sort of associates the sense of scent with one of the things that triggers memories most strongly. So how is this modeled in TensorFlow? Well, basically in TensorFlow and in machine learning in general, this is modeled as every neuron winds up being a data point. In TensorFlow, it winds up being a tensor. These tensors have sensitivities for the various inputs. So let's say that you're looking at a 10-question health survey. you might have 10 input tensors, each of which is attuned to each of those questions on the health survey and the answers to it. This is sort of like, to put it in physical terms, you've got nerves in your fingers, and some of them are, for heat, some of them are for pressure, some of them, so on and so forth. So different nerve endings for different input capabilities. Then you have biases, which are constants that are added to that output. So once again, to put it in terms of the human body, there are some things like sharp pain that sort of take a short circuit to the brain. There are other things that take a longer passage there. That would be sort of more like biases. This is sort of graphically what that would look like as an artificial neuron that gets in a set of inputs, and then it weights them, and it has a bias that it uses to feed to what's behind it. Notice I said what's behind it, because nothing is ever this simple in the real world. You can have a case where you have a set of neurons for all of your inputs, and then immediately behind that is a set of neurons just for your outputs, which are the possible outcomes. So if we continue on with the health survey example, let's think of the outputs as like, perfect health, diabetes, cancer, different things, obesity, different things that can happen as a result of different health decisions. But in actuality, it turns out that if you just have those two levels, you don't get as much accuracy as you're likely to want. So the most common model that you see is a convolutional neural network that has layers of neurons, aka tensors, in between the inputs and the outputs. And what these neurons are responsible for doing is looking at the data in different kinds of aggregations. And they evolve their aggregations over the course of different training data also. So, if you think about it, I talked about how you have neurons, for pain and for pressure and all that sort of stuff. Well, one aggregation of that is your sense of touch, right? And then you've got neurons in your eyes that are specialists in everything, but they aggregate as a sense of vision. In TensorFlow, the best example is with image recognition. You can create a neural network that just has neurons for each of the pixels, and then an output which says, this is a mammal or this is a fish. That'll work, but it won't give you much accuracy. What turns out to work more accurately is if you have an input layer that looks at each pixel, and then you have some layers behind that that aggregate it, and they wind up specializing, like if we take the example of the handwritten digits, some of those neurons in the middle will look like at the upper left-hand corner, some of them will look at the upper right-hand corner, some of them will look at the bottom. The ones that are looking at the upper left-hand corner, maybe those become specialists in recognizing the number 7, because the 7 has a very distinctive sort of horizontal line in the upper left-hand corner. The ones that look in the middle bottom, maybe those become specialists in spotting the number 1. So it's basically a sort of evolutionary process. Setting up all of those tensors by hand, if you were to do like we did in our first demo where we actually manually poked in the tensors, you could do it in Java. It would take you thousands of lines of code, but you could do it. So maybe that's a challenge for you as listeners. You can do that in your free time. But there's a DNN classifier that does all that work for you, and it does it very, very simply. So I don't know if anybody can guess what comes next in this story, but it's not in the 20% either. So in this case, what we do typically is we take a pre-trained model, like the output of demo 2, and we read that in, and that's what we actually wind up using to do our prediction. Now, this fits the common real-world team structures, and I guess that sort of speaks to a question that I was actually just asked one of the sort of speaker conversations earlier a couple days ago, which was, why do I think it is that we've got this 20%, 80% split? How did they choose the 20%? Really, personally, I think that the thinking was that the Java piece is going to be used more on the prediction side than on the training side, because typically, the training piece winds up getting done by folks who are more in like a data analyst, data scientist role. And the thinking is that they might do the actual training, then give you the model and ask you to do the predictions against it. So this does fit a common real-world team structure. Just FYI, in case anybody is interested, The code to actually do the training tends to not be complicated. I've boiled it down for this example as much as is humanly possible. I can show it to you in the discussion area afterwards if you like. I just didn't want to be pulling up a bunch of Python code in a Java conference. How did I previously train it? Just in terms of a theoretical model. You pass in input A, input B, input C. So A and B are the two things that we're either going to add or subtract. C is the output of that, and then I put a label on it. So basically, I poked in 1,000,000 examples of subtraction, 1,000,000 examples of addition, all of them labeled, pushed that through a neural network, and at the end I said, okay, you've seen all these examples, you tell me now when I pass in A, B, and C, whether that's addition or subtraction. This, sort of the next level evolution of our ability to do trainings. So here, we're going to look at a new class called Saved Model Bundle. So let me sort of compare and contrast this against Demo 2. In Demo 2, we loaded in a graph that had a gradient descent optimizer in it, and then we trained it within Java. Now we're taking the next step, which is we're actually taking a model that was already trained, and we're loading that in, and we're going to use it to do a prediction. So having said that, let's check out Demo 3. Oh, and I should say all of this code is available in the GitHub repo, which is on the slide at the end of the deck. So if any of you want to grab this code and take a closer look, be my guest. So there, that's us importing the new. Once again, notice it's in the org.tensorflow package, so nothing difficult there. And we use that saved model bundle, and we call load, and we load in the point in the file system where we've unloaded the model, which has been, in this case, theoretically given to us by a data scientist coworker. Then, on runner, we call the feed operation again. But something very important to note in this case, you see these names? These are sort of like the default names for input values assigned by this DNN classifier class. So I'm passing in 75, 25, and 50, and I'm going to ask it to tell us, if you see 75 and 25 and 50, do you think that 75 and 25 produced 50 by doing addition or subtraction? That's basically what this is going to be. This is another special name. This is where you get your answers. But there's a hint in the name here of probabilities. When you get into neural networks, remember, they can have multiple answers. So in this case, it's like addition or subtraction. I could have made it addition, subtraction, division, multiplication. In that health survey example I gave, it could be a whole set of possible health outcomes, and maybe in some different kinds of aggregates, like, this person got diabetes and cancer, or this person, is completely healthy, or you can have different aggregates. So what you get out of a neural network, and the DNN classifier in particular, is an assignment of probabilities for each of those outcomes. And we're going to see with this output that the probabilities wind up basically being certainties, but just want to explain why that structure is the way that it is. So we wind up getting back our answers. We put it in an array of 3, and the reason for those 3 positions is that position 0 will be the likelihood that it's neither addition nor subtraction. 1 is the likelihood that it's addition, and 2 is the likelihood that it's subtraction. So if we pass in 75, 25 with an output of 50, I think we can all agree that that's subtraction. Let's go ahead and run this and hopefully see that this assigns the probabilities that we would hope for. Okay, so here's our output. Possibility of it being neither addition nor subtraction, a really, really small number. You see the E minus 38 there? Minuscule. Possibility of it being addition, another minuscule number. Less minuscule, but still nothing. Possibility of being subtraction, 100. Because these are all fractions of 1, so 1 is 100. So it's basically said, boom, yep, I know, you've trained me, that's subtraction. Let's go ahead and just make this 100, which is addition. Go ahead and we'll rerun it. And what we want to see is that that 100% moves, yep, so 0%, very small number, 0.9999881, which, more often than not is as close as you can get a machine learning model to say that something is a certainty. All right, so that's demo 3. Let's go ahead and proceed to our final demo, and then maybe hopefully we have time for a few questions. So deploying trained models. So now let's think about the case where we want to put this in production. Chances are we're not going to run this. We're not going to run our predictions in the same infrastructure that we ran our trainings, right? You can, but it's unlikely. So before TensorFlow 1.8, you had to basically delve into Python and you had to use something similar to a library called Flask. That was your best option. Since TensorFlow 1.8, there's something called TensorFlow Serving, which is just built into TensorFlow. And there are few things in machine learning that could be simpler than this. Basically, show of hands, how many folks have worked with Docker before? All right, it looks like about 60% to me, so I'll give a short explanation. So basically, what we're doing here is we're building a very thinned down virtual machine, and we can build it on the basis of a very simple text file that describes everything that we want to bundle into that virtual machine. Although it's not really a virtual machine, it's something a little bit more complicated than that, but let's think of it in those terms. So this is the Docker file. Truly, these 4 lines are all that you need to deploy a trained model to make predictions. You do from TensorFlow Serving, which means grab the base TensorFlow Serving model, image off Docker Hub, copy the place where I have, in my local file system, put my trained model, which is exports / and then that long number, and put it in my Docker image under /models/model. Okay? Then you expose port 8500, which is for protobuf calls, and port 8501, which is for REST calls. Boom, you're done. That's your Docker file. To build that, docker build-t, give it a name, package up just that Docker file, and that'll grab your model and put it in. To run it, you do that command, and you're up and running with something that can receive protobuf requests on 8500, and it can receive REST requests on 8501. You want to run this on more than one machine? It's Kubernetes friendly out of the box. So spin up n number of images on that on Kubernetes, put a service in front of it that exposes 8500 and 8501. Now you've got a farm ready to do your predictions. So this is believe it or not, this is actually the easy part. One thing, this is the only thing in Python that I just had to show as a part of this. This line here, saved model cli.py show dir, then the directory where you put your model -all, that will give you the exact REST signature that you need in order to invoke your model using REST. So that is how I got the message that we're going to pass in this final demo, which basically uses REST to call our predictor running in Docker. Okay. Final demo. I want to show you, in this case, the most important thing is to understand I don't have any TensorFlow in this application. This is just your pure HTTP stuff. I feel bad that I didn't make this asynchronous after having seen the talk on Java 9, 10, and 11 yesterday, but I'll do that in the next version of the demo. And all this does is it takes this class I've created, which has 3 parameters with names that I got out of the model by running that Python command I saw earlier, passes in the same values as before, gets back the answer, and prints it out. I am running TensorFlow Serving in this window here, so let's go ahead and run this. Oh, hang on a second. was very proud of myself, but then I realized I ran the wrong demo. All right. So it gives us back a little bit more elongated JSON message, but if you look at probabilities, this should look familiar. 99.99988%. All right. So, in conclusion, what we learned how machine learning works. We learned what TensorFlow is. We learned where to get the required libraries, how to obtain, train, and invoke TensorFlow models, all from Java. What comes next? Getting more of the missing 80%, hopefully. Advanced model creation. Unsupervised learning we didn't even touch on, but that's a way you can do learning without labeled data. Now remember, this whole thing is open source, so if it really bothers you that the gradient descent optimizer isn't there, or the DNN classifier, it's just C++. You could go in and you could create GNI calls to wrap that whole thing and contribute it. It's not a problem. I think we have time for a few questions. I did want to say, you've got my email addresses below. You've got my GitHub instance there. Thank you very much.
Thank you, Derek. I think we have some time for several questions. Господа, если есть вопросы, поднимаем руку, я подойду. Так.
I told them everything they could possibly want to know.
Can you please tell us something about the projects where you used the machine learning?
I can tell you about projects that I have seen out there that have used machine learning. I'm sort of under NDA and all that sort of stuff. So I think one of the examples, so there are a few examples I gave, but I'll sort of organize them into broader categories. Recommendation engines are huge uses of machine learning. We tend to think about it in terms of, because you're interested in watching this on Netflix, maybe you're interested in watching that, or this song or that song. But it really winds up becoming a source of marketing for a lot of organizations to say, we notice that customers of this type tend to be interested in these products, so it becomes a source of marketing. There's stuff out there that will take a look at, it can automate some financial processes to figure out, this sort of customer might exhibit these sorts of behaviors, therefore here's like the sort of funding that will sort of best match their needs. I've seen that sort of done out in the industry. Health research is huge for it. And something I didn't touch on at all, but which is another huge use of this, is semantic analysis. Basically taking bodies of text and assuming that it's been tagged properly, looking at those pieces of text and saying, all right, this looks like angry text, this looks like happy text. You can do a whole bunch of stuff with automating customer support through that sort of thing. And most organizations have ready access to that anyhow, because if they're on Twitter, if they're doing any sort of tracking of call outcomes versus inbound communications, they've got, okay, yeah, this customer was angry, this customer was happy, so on and so forth. So they can do all of those sorts of training. So those are just a few of the things I've seen out in the industry.
Thank you, Derek.
Thank you.
And one more.
Hi, thank you for the talk. I want to ask if you think there is a demand in the industry for the Java SDK for the machine learning, and is there any push to get the 80% to where they should be, or is there just nobody needs it? Thank you.
It's an excellent question. I think it really has more to do with the way that teams are set up right now, that the training winds up being done by people who wear the data scientist hat. And this is just my sort of take on it. I think that this SDK is looking at from a perspective of lots of organizations have existing Java code bases, which are out there and working and in no need of replacement. So I think that Java is still thriving and still growing and all that sort of stuff. But if you think about the context in which you're going to do a prediction, that's most likely going to be in the context of an actual customer interaction or some sort of business process on the back end. What you really need in that case is the prediction capability. And so that's what they've really focused on in this 20%. It's not necessarily that there's any sort of Java decay around there. It's just that they didn't think that was the focus. The one thing I didn't get a chance to show as a part of this was doing a protobuf-based invocation across the wire. Didn't seem to me like it was terribly necessary, but there's a lot of stuff in the 20% that focuses on how you serialize and deserialize protobuf messages to get predictions from some system that's running out, elsewhere.